Welcome to my code demonstration of the drone detector. So for this demonstration, I'm going to keep it pretty concise as much as possible. I have quite a bit of code here, considerable amount, at least to step through in one video. So I'm going to be focusing on the most relevant and main functions of this program. And that will be the drivers for the chips and the screen, a little bit of the buzzer. But to demonstrate, I'm actually going to debug and step through the code on screen just to demonstrate how it runs. So you heard the tone. It's running. Oh, okay, I guess I can have that many breakpoints. So let me try that again. I had way too many on there. All right, back on track. I'm going to debug, and we're going to stop these breakpoints, and I'm going to explain what's going on. Okay, now I'm going to run you through. I'm going to hit resume, and we're going to go to the breakpoint in my initialization for the CC2500 chip. Okay, so this is the initialization. We can see there's a short delay, and then here I'm pulling the CS pin high, and then low, and then high again. The strobe, it sets it to receive mode. There's another delay. Here I'm applying the configuration. I'll actually jump into this one for you, show you. This is setting all the registers in the CC2500 chip, which is quite a few. This is configuring it to do what I want it to, because it's got a lot of different functions. Now we're going to step over. Apply config. We're setting the strobe. Again, we're setting it to receive. It was set to configure before, and now it's set to receive. I misspoke before. The first thing it sets to is configure. Now it's setting it to receive. And then we're going to recalibrate the noise floor. So this is one I'm also going to step into because it's pretty cool. So I first of all display a calibration message on the screen, and then I create my temporary variables. This is a number for the channels. I picked 100 channels on 2.4 gigahertz frequency that are common for drone usage. These can be changed. And then I have my logic for stepping through all of them. And so basically it sets the channel, delays, gives it time to change. And then it's going to read the RSSI port, which is the signal strength. And then it's going to sum that signal strength into RSSI. And then this loop sits and runs 100 times until all through 100 channels have ran through, and then it averages out the average of all of those readings across those channels and creates that noise floor here. Then this detection level threshold that I have right here is basically your sensitivity of how sensitive the device is going to be to spikes in that frequency. And so this can be tuned to make it operate more smoothly. Now I'm going to fast forward to my next breakpoint. Okay, so when it comes to actually scanning the sweeping across the channels of the 2.4 gigahertz frequency range, this is how my code, my software works. It sets the channel, it reads the RSSI, and then if the RSSI is greater than the detection threshold, clears the screen, and it displays what channel it is, first of all, and then it displays a detection flag. And then it turns the buzzer on with a specific tone, which I'll show you that in the buzzer driver. And then we have that same channel. We're going to make sure it's still on that same channel. And then we have a delay, read the RSSI. If, again, that's still a spike, we're going to display this message again and play the tone again. So this is more just a confirmation. If it's one temporary spike, it will just do this really quickly. If not, it's going to display twice, and it's going to be very obvious that you're getting that double confirmation because there will be a break in the tone, and it'll be a double beep instead of a single beep. And then a double beep will repeat as long as there's a spike. If you just get one beep and you only hear it once, it's not a double. That indicates that it was maybe a false positive or just a fluke. We have our else condition, which is just resetting the screen to how it was and turning the buzzer off. So the buzzer will be on until it's not detecting a spike anymore. And so I'm going to continue to the next point in code, which is sweep and detect once again. So I'm going to stop there, and I'm going to take us over to buzzer.c. So this is the buzzer driver. It's really simple. It's an active buzzer, so we've got this driver to pulse width modulate the tone that you want. Pretty simple stuff. That is our startup code. I've got a driver for the LCD screen, which this one has quite a few functions. We've got write nibble, send command, send data, initialize, write string, set cursor. I use set cursor pretty often, and then obviously write string and the clear function. These are all fairly simple, standard I2C, just lightweight, bare bones. And then I'm going to show you the noise floor calibration for the logarithmic detector. This is in main because it's a much smaller function. It doesn't require any configuration really. It just is establishing the noise floor. So I'm going to scroll down and find it. Here, yeah, right here. Log detector, recalibrate noise floor. Long name, but it works. Same thing. We're displaying calibration message, and then we're sampling through 100 channels. Well, not channels. In this case, it's just the wideband frequency, and we're taking 100 samples of that same channel. So it's slightly different. But then we're just making an average from that, setting our noise floor, and then setting a detection threshold. It's pretty sensitive right now, 0.07 of a volt. The detection is what it's set to. And we're going to continue the rest of the code, and it's going to stop again at sweep and detect. All right, so you see that it's got about a second rotation between these two frequencies and detecting. It functions almost like a radar where it scans this band. That's what I was going for anyways. It's not like a radar because it's not a radar. But on about 1 second interval, it's going to switch between those two channels and scan back and forth, alerting if there is detection. Every time the code restarts, we got recalibration and reinitialization. So every time the device is turned on, it's going to recalibrate both the log detector and the CC2500 chip for the 2.4 gigahertz and 5.8 gigahertz range. And then I do have an interrupt set up. Let me pull that up really quick. And it's pretty simple all the way down here. This I used for debugging to confirm that the CC2500 chip was actually working. So when I hit button 1, it's the integrated button on the STM32. It interrupts the system and it performs this test to ensure that that it's actually going to run as it should. So I'm running the code and I'm going to interrupt. I got to run it again. Get rid of this. Can't run it again. Interrupt. Okay, that brings us to our interrupt. I have a breakpoint set at run signal test. So we're going to jump into that. Now, the run signal test is almost like a sweep and detect, but instead we are seeing if the threshold is changing. Basically, if the inputs are changing and if we're getting different ones. And what we're seeing right now is that the chip is broken, which I talk about in some of my other materials like the report and the demo video. I had this work a few times, but something's wrong with this cheap Chinese clone that I got. But the code is sound. And when I use this to debug, I would go and I would let it finish its course. Put a breakpoint here. And wait for it. It must have stopped somewhere on one of my other breakpoints because I have it call a few of these functions. But basically I would sit there and test if detected was true. And if it's true, that means it passed the test. If not, it means it didn't pass the test. So it didn't, clearly, because we didn't stop. Um, we didn't reach this break here. So it continued and then it finished. No success there, and that's because the chip fried itself somehow. I think I might have been getting some backfeeding, or maybe it was just cheap garbage, which is probably most likely the case. Anyways, this is my code demo, and there's more to it. If you're interested, you can look on my GitHub repo and read through the rest of this code. A lot of what's here in main is from the IOC tool in Cube IDE. As for the logic in my drivers, those are 100% me. They're not made by the IOC tool in Cube. Yeah, that's it.